This video is on spring mass systems. And just before we get into it, I'm going to go back and review these equations. These work for all simple harmonic motions, which includes pendulums. That frequency is the number of oscillations divided by the time it takes for those oscillations. T, which is period, capital T, is 1 divided by the frequency, or the inverse of the frequency. And frequency is the inverse 1 over the period. So these equations work for spring mass systems as well. This is a spring mass system. Imagine a frictionless surface. You have a spring attached to the wall here and a mass attached to the end of the spring. The spring has a spring constant lowercase k and it has mass m. And the units for those two are written down here. Kilograms, this is newtons per meter. The way a spring mass system works is when it's at rest, so here's the spring and here's the mass. When you bring it to a stop, it's at rest. And we'll call that position 0, where the mass is at rest, the equilibrium position. And if I take this mass and I stretch the spring, I pull the mass up to this place here, and I let go. Again, we're going to have simple harmonic motion. There is a restoring force that wants to bring this mass back to equilibrium. The spring is stretched, so there is a force, given by Hooke's law, which will pull the mass, accelerate the mass back this way. The mass will pass the equilibrium position and then it will compress the spring. And at this point, we'll put a force backward and the mass will get pushed back this way and back and forth. It'll go past the equilibrium position and just go back and forth. That's the spring mass system. So yeah, let's come down here. Let's go over some equations that we use with these. You pull the mass and release it at time t equals 0. That the position of the spring mass system, or the position of the mass as a function of time, is given by this equation. So the position is equal to it's a cosine omega of omega t, where a is the amplitude or the maximum displacement of the spring mass system, and omega is the angular frequency, which is simply related to the frequency. So going back to this picture, let's say I had extended the mass, I don't know, to some position here. Let's do this real quick. Let's say I had brought it out to like, I don't know, 2 meters or something. Well, these are all in meters, but let's say I brought it out to 2 meters. This is the amplitude, where A is 2 meters. And when I let it go, it'll go over here to negative 2 meters. So this end and this end, these are the maximum displacement. But of course, the spring mass system will pass over other intervals, 2.5, 1, 1.5, and then going negative, negative zero point 0.5, negative 1, negative 1.5, and all the way to 2, negative 2, negative 2. And so this equation, you plug in what the amplitude is. If you had taken it to position 3 and let go, well, the amplitude is 3. And you plug in how much time you're wondering about, 1 second after you let go, 2 seconds or whatever. And as long as you have the angular frequency, you can figure out the position. So a couple of useful equations for angular frequency is okay, let's do that. The angular frequency squared is equal to the spring constant over the mass. Um, that's one equation we'll need. And I should have started with this equation, that the angular frequency is related to the frequency, 2 pi times the frequency. They're just related. But yeah, so the angular frequency squared is equal to the spring constant divided by the mass. If you put more mass on this spring mass system, it makes sense that you've increased the mass, that the angular frequency would decrease. Um, so you put more mass on this, you bring it to the same amplitude, and you let go, and yeah, it will be moving with less frequency. I would say slower, but I'm not talking about speed. Um, the spring constant. If you put a stronger spring on there and you set it in motion, um, if the value of k is higher, then the angular frequency increases. It'll go back and forth with a higher frequency. Cool. And so we'll need those equations. And if we combine some, no, I'm not going to derive it here, but if we combine the equations that we know of, we arrive at this relationship that the period of the spring mass system is equal to 2 pi times the square root of m over k. And you can derive that equation by using these two equations and then using, this relationship, which we talked about before. You can derive this equation yourself. All right, cool, let's keep going. So have I summed up all of the equations so far? Yeah, okay, those are all the equations. Oops, and I kind of left, these notes here. That's okay, you should copy these down. This is the same picture we looked at earlier. When x is at the positive amplitude, in other words, when it's at the amplitude on the positive end, and this thing is in motion, at this position, it actually has zero speed because at one moment it's moving to the right, and then it's about to move back to the left, and it'll, for a moment, for an instant, it will be stopped. Um, so it has zero speed. When the mass is moving past the equilibrium position, that's actually going to be the maximum velocity of the spring mass system. We say positive or negative. If it's moving to the left, of course, that's negative. And when it's going back and moving to the right, it's moving to the right with the maximum velocity or maximum speed. And that's at that position. Over here, again, the speed is zero. On the other hand, when we talk about acceleration, as the mass is, when it's at the amplitude over here, it actually has the maximum acceleration. And we say negative because it's being accelerated back this way, which is left. And when it's in the middle, although it's moving at the fastest velocity there, its acceleration is zero. And then over here at this other end, when it's at the negative amplitude, again, it's being accelerated back in this direction. That's positive A max. And so there are some equations for the maximum velocity and the maximum acceleration. So let's write these down. Vmax is equal to omega times the amplitude, and Amax is equal to omega squared times the amplitude. And what else? Yeah, we have two more. Okay, sorry, three more. The energy of the spring mass system. We're going to write it down over here. Remember that energy is, okay, normally we say UG, we have kinetic energy, and then we have spring potential energy. Um, the way we've drawn it here, it's all at the same height, so let's just get rid of that. And so really we're just talking about K plus US. So this would be mv squared over 2 plus kx squared over 2. So that's another equation we can use for the mechanical energy. I said energy earlier, the mechanical energy of the spring mass system. Um, When the mass is at the positive, or when it's at the amplitude, its velocity is zero as it comes to a stop momentarily. So at that end, this term mv squared over 2 is zero, and we're just left with kx squared over 2, but x is at a. So another equation we can use for the mechanical energy is ka squared over 2. And there's yet another way we can write this. When when the mass is in the middle, okay, um, it has its maximum velocity there, and the spring is not stretched at all because it's at the zero position. So then the spring potential energy term is zero. So we would say m v max squared over 2. And so the last thing I would say about these is there is some confusion. Some students get confused about this. Um, you can put in v in there, you can put an x in there, but like what you don't want to do is you don't want to do like mv max squared over 2 plus ka squared over 2. I've seen people do this. Um, so yeah, oftentimes, okay, just I would say use these if you can. If you have the amplitude or if you have, Vmax, I would just say just opt for one of those. And I'll keep it simple like that. Cool. So how many equations do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. Wait, 1, 2, 3. Yep. Um, Sometimes I put Hooke's law on this list. It shows up on one assignment somewhere. It shows up in places. Let's do an example. 3 kilogram mass is attached to a spring with constant 600 newtons per meter. The mass is displaced 20 centimeters and then released. So question A is what is omega? And so okay, yeah, we have mass and we have K. So we can use omega squared is equal to K over n, which means that omega is equal to the square root of K over m. And so that's 600 square root of 600 over 3. 14.14 or 14.1 radians per second. That is the angular frequency. I don't know why that happens. Cool. Part B, what are we finding? Period. Yeah, there are many ways to solve these. I'll just go for the straightforward way. This is 2 pi square root of m over k, which is 2 pi square root of 3 over 600. 3 over 600. I think I did that right. 3 over 600, yep. So I got 0.444. Period is 0.444 seconds. It's probably, but that's fine. Cool. Let's find C, A max. We have an equation for A max. It's omega squared times A. So omega is 14.1 squared. We do know the amplitude. So the mass was displaced 20 centimeters and released. That is the amplitude because where you extend it and let go, that's going to be the amplitude. But that needs to be in meters. So that would be, 20 centimeters divided by 100. That's zero point 0.2 meters. I already forgot it was zero point 0.2. 39.8 meters per second squared. Okay, just checking. Oh, what's next? D. What is the mechanical energy? Um, yeah, so I said earlier, if you could take advantage of, we don't have Vmax, we have Amax. So what was the equation? I'm sorry, we have amplitude. So let's use E equals K times A squared over 2. K is 600. The amplitude is zero point 0.2 squared over 2. 12. Why does it keep doing that? 12 joules. And let's figure out E, which is what is the speed? What is the velocity when the mass is at x equals 0.06? It's only one equation with V, I believe, which is this. So that's 12. The mass was 3. Okay, we don't know V. 600, I think. Yeah, 600. What was the position? 0.06. Okay. 1.08. So 12 minus 1.08. Oops, 10.92. Cool. Times 2 divided by 3 times 2 divided by 3 square root 2.7. Sounds good to me. Cool. And there it is. All right. Okay, I should probably go over this as well. These are simple harmonic motion graphs. Yeah, I'll go over one of these. Yeah. Or no, I'll just go over everything. Okay, so um, this is a simple harmonic motion graph. In other words, you have a spring mass system, and this is showing its position over time. And it's sinusoidal, okay, because the spring mass system will, oscillate back and forth, but over time it'll make that shape. So let's figure out the amplitude. At time zero, or really what you essentially want to look for is the highest point of the graph, because that's the maximum displacement from zero. That's the amplitude. And on this one, it looks like this is 0.5 meters. Do my work over here on the side for frequency. Again, there's many ways to solve these things, and so uh, I'll show you a few ways to solve these things. We can do number of oscillations over time. And so we need to be able to count an oscillation. And here's the pattern. The spring mass system will start at the amplitude, it'll go to the negative amplitude, and then it'll come back to the positive amplitude. That's one cycle or one oscillation. Remember, it's got to go away and come back like the pendulum. So, two ways we can do this. We can count one oscillation and look at the time if there's a nice time there. So that's 1 over 1. Or you can look at the whole graph and count 1, 2 oscillations over 2 seconds, which I think I'll do. Do it like that. And so that's 1 hertz. Hertz. For period, you could take the inverse of the frequency, and I realize mathematically this is not very exciting. 1 over 1, which is just 1. So you can use an equation to find period, or you can just look at the thing. How much time does it take for one oscillation? Well, that's 1 second for one oscillation, right? That's what period is. So you can just look at the graph. Um, cool. Let's do another one. Okay. This time the spring mass system is starting from position zero, but let's figure this out. So the amplitude, maximum displacement from zero is 1. There we go. Let's figure out whether you're doing frequency or period next. You need to know what a cycle looks like. You can still do from here to here, but there's no convenient times for you to use there. So we're kind of forced to look at it another way. This is an oscillation. Let me use this here. This is an oscillation. That's one oscillation. So it will go, from zero, it'll go to the amplitude, it'll go back through zero to the negative amplitude, and then back to zero. And so you just want to memorize these shapes. Like here's one shape, that's one oscillation. Another way of looking at it is like this. And so we can do uh, frequency is number of oscillations over time. So again, you can do one oscillation and divide it by that time, or you can do the whole thing. I'm going to count 1, 2, 3 oscillations over 1.5 seconds. And so that should be 2 hertz. And if I messed up on the math, just write it down with the correct number. Okay, period. We can just look at it, look at one cycle and say, okay, it took 0.5 seconds. Of course, you can also show work for this. We can take 1 over the frequency, which is also 0.5 seconds. Cool. And I think you guys get the idea. This is another pattern you should look at. It's really the same pattern. It's going to go away and it's going to come back. That's one oscillation. Now, there's no convenient time here. So if we did two oscillations, there's still no convenient time. But in three oscillations, you know, it's 3/2, which is 1.5 hertz. Cool. And then the period is just 1 over the frequency. So 1 over 1.5, which is 0.67 seconds. Well, I'm not too proud to check. Let's check. Yep. Okay, the amplitude for this one is 3 or almost 3. Anyway, we're going to say it's 3 meters. Cool. I think you guys get the idea with those. And I might as well just finish up. You can do the last one if you want. Um, that's not a complete number of cycles. So like if you wanted to do that one, you'd have to go, that's 1, and then that would be 2, and this is a half. So that would be 2.5 cycles over 2 seconds. And you could figure that one out. What I do want to show you here is how to go from a position time graph and create a velocity time graph and an acceleration time graph. And so we'll do that real quick. So the strategy is figure out the maximums and figure out the zeros. Actually, we'll figure out the zeros first. So where is velocity 0 on for a spring mass system? Where's velocity 0? And we covered that earlier in this video. Now, when it's passing the equilibrium position, it's actually at a maximum. It's here and here that the velocity is 0. And so when we know where to put the zeros of velocity, it's going to be here, and it's going to be here, and here, and so on. Where is the velocity at a maximum? Well, it's here, so that's Vmax, and it's plus, because it's going to the right. This is a Vmax. It's crossing the equilibrium position. That's negative Vmax, and so on and so on. So we'll need to put a positive Vmax at zero point 0.5, and we'll put a negative at 1, and just continues. Yeah, right here. Yeah, it started with a negative Vmax. Cool. So trying to draw a sinusoidal curve is I'm still working on, and especially on this tablet here is a bit difficult. So you may want to go over it a few more times and make sure it's good. If you're using pencil, you can erase. Yeah, it's supposed to look like this above, which is kind of hard for me to do on this tablet. Cool. Now let's create the acceleration graph. Again, we'll look for maximums and zeros. The acceleration is at a maximum. Well, let's talk about the zeros first. Here's a 0, here's a 0, here's a 0, because the acceleration is 0 at 0 position, at the equilibrium position. So we'll put a 0, a 0. Okay, where are now the maximum accelerations? It will accelerate maximally here and here and here and here. And so This is positive A max, this is negative A max. Because it's shifting positive, here it's shifting negative, and so on. So let's see if I can do this. So between 0 and zero point 0.5, that's a positive. Between 0.5 and 1, that's a negative. And it will alternate like this. And then we'll practice drawing our sinusoidal curve. I tried. And if I let it go, of course, it does something silly like that. Okay. I'm not setting a good example, but this is the pattern we're trying to get here. It's much easier on paper, believe it or not. Actually, over time, doing that back and forth, it actually looks pretty good. Okay, cool. This is the last bit of the notes. Let's go from a position time graph to a kinetic energy versus time graph. So, okay, kinetic energy, whoops. You can have a zero speed, but you can never get a negative term out of this because it's squared. You can have zero mass, but you can't have, kinetic energy can never be negative, is my point. So at best, it can only be zero. And when V is zero, that's when the kinetic energy is zero. So V is zero here, and here, and here, and here, and here. And so here, and here, and here, and so on, is where the kinetic energy will be zero. It will have a maximum kinetic energy where it has the Vmax here, 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 here. And it's never negative. And we might as well say here. So that's here, 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 here. Now, the graph is not exactly sinusoidal, but having said that, let's just draw it kind of sinusoidal. Oops. No, I'm just going to keep going. Really hard on the tablet. I don't have any leverage on my hands, so I'm just kind of going with it there. So you'll have to excuse that. And then potential energy. Well, that's when the spring is compressed or stretched. So when the position is zero, it has zero spring potential energy. So we'll just say here, 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 here. These are all zeros. Spring potential energy can't be negative either. It can only be zero. Here is maximum, and the reason for that is it's kx squared over 2. And yeah, nothing can ever be negative here. So in between is where we have the maximum spring potential energy. So here, here. We'll notice that the two graphs, sorry, I'm just going to go fast because it's going to look bad anyway. You can't tell, but I do have a higher expectation for you when you draw these. It is much easier on paper, so do a better job than what I'm showing you here. You should notice that these two graphs are flipped, right? And they should be. The mechanical energy is that one. That's the mechanical energy. Now, real quick, just to show you one last thing, but I'd never try to do it this way. I sometimes use this to verify I did the right job. You'll notice that the graphs all look like this sinusoidal shape. The velocity time graph is shifted. If you draw a line here about a quarter of a cycle through, you will tell that from here is what the velocity time graph is. Shifted a quarter cycle there. And the acceleration time graph, if you take the position time graph and just flip it, or I don't know the math term for this, but you just flip it around, that is the shape. You go from, sorry, you go from this and you flip that so it looks like this. That's the shape of the acceleration time graph. But use this strategy of maximums and zeros. And I start with zeros first, it's a little bit easier.